Good morning, everyone, and thanks for having me. The okay, so this talk is going to be based on a paper that we uploaded recently, which was written in collaboration with Matt here, Rajat, and Clemo, who were here last week. And the plan of the talk is to sort of understand what is done in the gauging invertible symmetries, and then draw parallels to cases for non-invertible symmetries and the developments that we would need to make in order to have a complete theory of gauging non-invertible symmetries in 2+1d. Let me start by briefly reviewing modular tensor categories and TQFTs. So, modular tensor category is a mathematical structure that captures one-form symmetries of a 3D TQFT. So, the data that goes into specifying a modular tensor category is as follows. You have a set of line operators. You have a set of topological line operators in your theory. Their fusion, and 3, something called their topological spin, which corresponds to evaluating the expectation value of this configuration. So A corresponds to a line operator in your TQFT, and we evaluate this configuration. And 4, something called braiding, which is the expectation value of hop flank. But again, A and B are your topological lines. So in a Chern-Simons theory, they could be Wilson lines, so on and so forth. And the fifth data is something called associativity. It's the F symbol for the fusion. So it's the isomorphism between the following diagrams. Which one? Yeah. Right. Yeah. They are symbols. It's the isomorphism between these two line configurations. So this would be equivalent to having tensor product of vector spaces be isomorphic to a different tensor product of vector spaces. But this is not going to be necessary for the purposes of this talk. In fact, F symbols are always they're always pushed aside when it comes to dealing with TQFTs. We can get a lot done just by looking at the S matrix and the topological spin. Right. Is everybody comfortable with the definition of a modular tensor category? I can do an example if necessary. Would anybody like to see an example for this one? Yes. Okay. Okay. Right. Let's look at an example. U1 at some level k, integer level, Chern-Simons theory in 3D. The action of this theory is the following. And the equation of motion is the field strength is 0. So there are no gauge invariant local operators in this theory. The only operators that you have in the theory are line operators and things you can construct with the line operators. And the line operators are of the form rather I should say loop operators, because since there are no local operators, line operators are not going to be gauge invariant by themselves. And here alpha has to be an integer for the purposes of gauge invariance, and the fusion in this case is the following. Let's say k is an even integer. The fusion is determined modulo k. So the line operators and their fusion forms a group integers modulo k. And their braiding can be deduced from the action. And this is because you can take the action, canonically quantize it, and we would recover. So So in order to evaluate braiding, what we would do is we would take this thing and try to evaluate the expectation value of the hop length. So if you now try to do this, you would try to pass the loops outside of one another, and you would pick up this contribution, which is what goes here, up to alpha and beta, because alpha and beta are the things that sit outside the loop configuration.
So the fusion takes the alpha and beta different, but gamma is the same gamma.
Yeah. So yeah, the way to think of this gamma would be to take a loop and then shift it in the perpendicular direction to the loop infinitesimally small, and then you take limit epsilon tends to 0. So this is braiding, and you can also show that the topological spin, so this is denoted as theta. So this is a simple example. In fact, there are simpler examples, but this will do. And the idea is simple. A modular tensor category is the chiral data of an RCFT. And we know from Moore and Seiberg that all the primaries of the RCFT extend into like bulk Wilson lines. And the correlators of the RCFT will have holonomies and monodromies, which are captured by these two quantities. And the F symbol is the associativity of the primaries. So yeah, this is in some sense the bulk boundary correspondence for 3D TQFTs and RCFTs. So yeah, this is the data of a modular tensor category, and that's a simple example. Yeah. Here. Really? I'm not sure. Okay, so this is a brief review of modular tensor categories. And now let's start by okay, yeah. So what I want to discuss now is, can everybody see this? It's under the shadow. Okay. I'll write here. So AG invertible symmetries. Right. So this is like a complete result, which was like understood, I think, back in 2007 by Ettinghoff, Nikšić, and Ostrich. And its application to physics and sort of working out the details in context of lattice models was done by these guys back in 2014. So it's a complete result. We know how to gauge invertible symmetries of TQFTs. So let's start by specifying the data that you need to define an invertible symmetry, and we can look into how we gauge it. So the invertible symmetry is defined as follows. Given a modular tensor category C, an invertible symmetry G is specified by the following data. So the first one is a homomorphism from G to braided automorphisms of C. So this just means that if there are a set of lines, then I can permute them around in a way that preserves braiding, topological spin, fusion, and all the other data. So this is the first one. And then the second one is something called a fractionalization. So symmetry fractionalization is just another word for how symmetry acts on your TQFT. So recall that whatever symmetry acts on is like a representation of the symmetry, and the representations can be linear or projective. And that's what symmetry fractionalization captures. It captures the projectiveness of your symmetry. And the third one is something called H3GU1, which is, okay, maybe I should write down the obstructions to this as well. So there is something called an obstruction to symmetry fractionalization, which is given by this group. This just tells you that if this is non-trivial, if this cohomology group is non-trivial, you cannot realize your symmetry projectively on the topological face. It also means that the symmetry sort of forms a two group with the one form symmetry, because everything we have in a TQFT are just one form symmetries. And so this H3GU1 is the so-called Dijkgraaf action. It's just a topological term that we can add to the path integral, corresponding to like actions for gauge fields. And but what is the most important one is that the anomaly of the symmetry has to vanish. In fact, it should have come first. So yeah, the things that we need to define an invertible symmetry action on a TQFT is first, we have a symmetry group that acts on the anions, it permeates them around, preserving braiding, and then the H4 anomaly vanishes. So once we have these two things, then we can worry about how the symmetry is realized on the TQFT, linearly or projectively, and we can also add action terms to the gauging process. So yeah, this is the data that's required to specify an invertible symmetry. And the way to gauge an invertible symmetry is known, but it's sort of complicated. What we first do is we take our modular tensor category C, and then we extend it so we extend it by adding twisted sectors corresponding to the symmetry action to the data of lines in a theory, and this is known as G extension, but there is a procedure which is related to crossing. So this is the G crossed extension. So we first include the twisted sectors, and by including the twisted sectors, I mean we add the twisted sectors by hand, and then we also need to figure out how these operators fuse, how they braid with the genuine lines, and their symmetry action, and so on and so forth. So include twisted sectors. This is first one, and then once we do this, we do something called equivalentization, which is identifying the things that are linked by symmetry together, which corresponds to gauging the symmetry. So corresponding to, so this is denoted right, and in these two papers they sort of understood this carefully and gave us polynomial equations that have to be solved, which would allow us to determine the S&T matrices of the gauge theory. But these polynomial equations are still hard to solve, and there is no clever ansatz that would allow you to simplify the process. And the goal would be to have achieve this sort of completeness for gauging non-invertible symmetries. In principle, we start from some sort of a symmetry that acts on your TQFT in a non-invertible way. We'll look at an example. And then have polynomial equations that you can solve to get the gauge theory, all the data of the gauge theory, without having any idea what the gauge theory looks like. And that would be the goal, but that is still out of reach. What we could do is simplify the question. Given, so this is the question, given modular tensor category C, which corresponds to some TQFT and some symmetry, it could be invertible or non-invertible. Let's say we know the gauge theory. We know the gauge theory to be some P. Can we explicitly understand the process of adding in extra defects, their properties including braiding and topological spin sort of emerge from the other direction? So we know that if I take some symmetry and then gauge it, I go to B. Now the question is, what are the twisted sectors and their properties? This kind of simplifies our program since we know the target. And we also know that if there is a zero form symmetry that's gauged to obtain a different theory, then there is always something called an anion condensation in the other direction. And anion condensation is extremely well understood from the perspective of mathematics and then physics. But I'm not going to get into anion condensation in this talk. But the idea is that since it's well understood, can we further make our arguments more precise for the gauging case? And that is the question we try to understand in the paper. So this is roughly, okay. Yes, G in this case is zero form symmetry. I should have mentioned that. Yeah, 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 exactly. Well, we won't try to solve the polynomial equations, but there is an easier way to do it, and we'll look at some physical like examples. See what's going. Maybe not Chern-Simons, but we could do that too. Yes. Yeah. Yes. But there are simpler examples, I think.
G will be a zero form symmetry. Yeah, I guess he has a line mostly discrete.
Yeah. B is the gauge theory. Right. We have time to do that, so yeah. Right, that's it. So let's first look at some example of symmetries in different TQFTs.
That's not the. That's not the. Normally, you would. The symmetry of the toric is just.
Yeah. Is
C2 times 2 is the center of C2.
Yeah.
It's C2 electric.
Yeah, it's just it exchanges the electric and magnetic line. It creates a force.
But also you can gauge very general.
Yeah. So the next one. It's like a 2+1.
Like if you go from C fusion category to center of C, I think what Frank did, it might be some discrete gauging of C rather than gauging in the center of C.
Yeah, that'd be a great.
Okay, so that's.
Yeah, so here he's gauging the bulk. He has 2+1d, say toric code in the bulk. Gauging the bulk. You get something for. So can't say that it's toric code.
Still, what is gauging then? Gauging is introducing some defects. But the spectrum of these two theories is still the same, isn't it?
No.
Because, for example, the gauge toric code has a dimension 2 line, dimension 2 orbit of the NF.
No, but the spectrum.
Spectrum of the
H is 0 here, I guess.
yeah.
H is 0 to the top one.
No, it's okay. If you do different lattices, it's not.
I mean, an example of like you can get from the trivial theory to any string net, but it's kind of gauging in principle. So like unless like I think you would say that all the different string nets could predict the fusion categories.
So we say motorically can go to any other state.
In principle, yeah.
It's not a verb.
Oh, okay, okay. So I just have in mind, okay, for me, gauging has to be.
Yeah, so his motivation is
Well-
see his thought is that
So it is invertible in the sense that you can do gauging, but it's not.
it's not like verb.
It's not like by gauging. So in general, you can, given any TQFT, you can go to any other weight equivalent TQFT by doing this kind of gauging. So gauging gives you precise.
Yeah, so I guess he'll hopefully get there. But yeah, it's not a verbal gauging. It's not gauging like.
Right. So toric code has already been mentioned. Let me just write down the MTC data for toric code. And if there are high energy people in the audience, the 3D action for toric code is the following. Yeah. I've suppressed the wedge symbols and it's just the BF theory. So in this theory, there are 4 simple line operators, the identity, and then the Wilson line for A, Wilson line for B, and then a combination for both of them. So these are the lines. And they have a Z2 times Z2 fusion rule. But it's usually easier to denote them as 1, E, M, and F. Following conventions. So 1 corresponds to the vacuum, there is no line. E corresponds to this, M corresponds to that, and then F is the composite. And the braiding is the following. It's a 4x4 matrix. It's unitary. You have and the topological spins are the following: 1, 1, 1, -1. So the F is an emergent fermion. It's a line operator whose topological spin is -1. And this is the MTC data for toric code. The F symbols and the R symbols are known, the F symbols are trivial. And one of the symmetries that Matt was mentioning was this Z2 EM duality symmetry. Which is the thing that exchanges the A Wilson line with B Wilson line. In fact, this is like a symmetry of the action. So P is exchanged with M. And this is a Z2 symmetry because you exchange E and M, and then the second transformation exchanges M and E, so you're back to origin. So this is a Z2 EM duality. And one could ask the question, so what happens if I gauge this symmetry in this theory? And the way to do it is to first, so let's denote the toric code MTC as TC. And sort of roughly follow this procedure here. Right, so we first extend TC by adding twisted sectors. So it's supposed to be Z2, so TC0 and TC1 such that TC0 or E and F, all their braiding data. And TC1 has two anions. They are not genuine anions, they are non-genuine lines. So sigma plus and sigma minus, if we were to draw a space-time picture for them, they would be boundary conditions. They would be boundary conditions of a surface, because a surface in 3D would be the one that implements zero form symmetry, that implements the Z2 EM duality, such that if an E line passes through the surface, what would emerge would be an M line, and vice versa. So this is TC1, and in fact, the way to show that there are two defects is done in this paper. And there are two defects here because of something called a fixed point theorem. I'll come back to this for the non-invertible symmetry case, fixed point theorem, which states that the number of twisted sectors of a symmetry is equal to the number of lines that are invariant under the symmetry action. So we added two twisted sectors because there are two lines that are left invariant. The EM duality only acts on E and changes it to M. It keeps the 1 and then the fermion constant. We'll revisit this shortly. And there is another constraint among G-crossed braided categories, that the quantum dimension of this is supposed to be equal to something called quantum dimension of that. And this just roughly means that, okay, I forgot to mention what a quantum dimension is. Quantum dimension. Right. So quickly, a quantum dimension is a number that you can give to a fusion ring. Just like when we have representations of a finite group or a continuous group, we can associate something called a dimension to the representation, which will satisfy the fusion rules for the representations. And this is a theorem which states that if you have any fusion ring, then you can give something similar to a number, like a quantum dimension that would follow the fusion rules. So if A tensor B is some C, this is like a fusion rule, then you can give numbers to A and B such that real numbers such that this thing holds. This is what a quantum dimension is. And for abelian, like this is an abelian TQFT, all the lines have quantum dimension 1. So D1 is 1, obviously DE is 1, DM is 1, and then DF is 1. But to preserve quantum dimensions in TC0 and TC1, D sigma plus is root 2 and D sigma minus is root 2. So we've added defects by hand, and okay, we can erase this part. The quantum dimensions again are this. Yeah, if you have a fusion ring, then you can just associate numbers which would satisfy it. So for Ising, the quantum dimension of the 1/16th would be root 2, because root 2 times root 2 is 2, which is equals to 1 plus epsilon. Yeah. That's true. Right. So this is, so far we have added the twisted sectors and we have constraints on their quantum dimension. With little more work, you can show that the twisted sectors have the following fusion rule. This is equal to sigma minus tensor sigma minus, and you also have this is in addition to the original fusion rules, which was something like E tensor E equals M tensor M tensor S equals 1, and then E tensor M equals F. So these are the fusion rules. And now there are other things like braiding and topological spin corresponding to which can be obtained by solving some polynomial equations, but this is hard. This is kind of painful. And there is an easy way to see what the gauge theory could be, and the hint is actually in the fusion rules. We see that this TC extended by Z2, which is the following. So it's 1E M F sigma plus and sigma minus have an Ising sector. So there are lines in this TC0 plus TC1, so the original theory plus the defect theory, that furnish an Ising fusion rule, which is exactly the sigma plus and sigma minus 1 plus F. And sigma plus is related to sigma minus by multiplying with an M line or an E line. So what we would have here is something like this. Exactly. Yeah. Yeah. So yes, we can discuss surface operators in just like a second. So this is what the extended theory looks like. It's the theory with its defects turned on, and we see that there is an Ising like sector. It's not quite Ising, but it sits there. In fact, the precise way to state this would be it's like there is some Tambara-Yamagami fusion category over the Z2 group, and depending upon the choice, it could be Ising or SU2 at level 2 or any other thing. So now what we can do is we can use a formula from category theory, which says that the gauge theory, which is some toric code, you first extend by Z2 and then you equivalentize it, is equal to the center, the center of this extended category with which is transparent to toric code, which is just, so this formula is just a clever way of picking out Ising times Ising bar. So what you would get at the end of, if we take this and then apply it here, what you would get is something like Z of Ising, which is Ising times Ising bar. And if you change up your like your fusion data, which corresponds to adding the action, it was here, I erased it, you could also get SU2 at level 2 box SU2 at level -2. This corresponds to turning on a Z2 SPT for the EM duality symmetry. And this is an easy way to figure out what the gauge theory is instead of having to go through all the polynomial equations. The rough idea is to figure out what is the fusion category that sort of appears there and then make contact with the gauge theory. And there is a way to justify this, but we can take a look at it in a second. Is this clear? What I've argued so far? I could show you the equations, but it would take more time. Yes. So this is how we do it for invertible symmetry. We first add twisted sectors, and then we get constraints on quantum dimensions just by using this fixed point theorem. And then with some work, in fact, there is an explicit formula which will allow you to calculate the fusion rules. You can compute what the extended theory might be, and you can also just stick with the same mechanism and compute the full gauge theory. But you can also use tricks available to you just by using the fusion ring, the idea of the fusion. So this is how we do it for invertible symmetry, and the goal is to generalize this for non-invertible symmetry. I have 40 more minutes, so yes, let me start. Okay, maybe this is required here. There is these parts. Mhm. You don't need to guess, but guessing is easier. Is what I'm saying. There is like an explicit set of polynomial equations that we can solve. It's just that it's too hard to solve them usually. Yes.
Yeah. And in the invertible case, that's like that is easier, but I guess like the case where the annual condensation is kind of like non-invertible, then you have to do a non-invertible zero form gauging to go back, and that's
Well, I assume you're going to discuss that.
Yeah.
Discuss the non-invertible. And I think actually we say the paper is much broader than this.
Yes. Yeah.
Separate topics.
But I'm confused. So you always get one form symmetries.
Well, the dual to a zero form symmetry, when you gauge a zero form symmetry,
Exactly.
you also one form symmetry. When you gauge a non-invertible zero form symmetry, you also get a form symmetry, but it's not the representation category of the group. So when he gauges the C2 symmetry, he gets rep C2 as a dual symmetry and I times I bar. Or generally, when you gauge something non-invertible, you get something which is not rep sheet. So he's gonna, it's just some algebra applying. It doesn't form a
But it's
closed fusion
okay, but
subnet.
it's still
We'll
just one
probably
form.
discuss it.
Yeah.
So which you can also rewrite as a surface, by the way.
So does that mean that if you and if you do this on the lattice, can all of this be done on the lattice?
Yes,
And then get stringlets.
yes, in these examples.
Well, you always get stringlets.
Well, not always, because what we're saying also works for chiral case. It doesn't say, I'm confused, like there's, well, I think there's, at least I have some confusion about how to do it on the lattice in the chiral case, maybe. I
Well,
think
no,
there you
that should not work, of course.
well, I think you have, the idea is you have a Walker-Lang model.
Yeah, but then you have to go to 1, 2,
Yeah,
2, 3 plus
yeah,
1 actually.
yeah.
say that it's known how to do it on the lattice.
I think, yeah, probably. Maybe we should discuss after.
Right. So let me mention non-invertible symmetry of Tori code. Right. So in order to construct this non-invertible symmetry, this was like the way to do this was that was done by the Hamburg people, or like some subset of these names. And then there was a recent paper by Shuang and collaborators, 2022. This is a series of papers, and they show us like how to construct a non-invertible symmetry given a TQFT in terms of a model latency category. And in this case, it only works for abelian theories, so let me mention that. So the starting point is that in 2+1d or 3d zero form symmetries are implemented by surface operators. So the way to get all symmetries of a TQFT, all the zero form symmetries, would be to construct surface operators. But as I mentioned earlier, in the case of Chern-Simons theory, and broadly in the case of all 3D TQFTs that are semi-simple, there are no gauge invariant local operators. There are no local operators. You only have line operators, the one form symmetries. In which case the surface operators would be constructed by taking a surface and then triangulating it with lines. And yeah, so roughly what we do is we pick a set of lines which are yeah, which have something called a separable multiplication that satisfy a separable multiplication. In fact, this specifies something called a separable algebra in your category. We don't need to get into algebras inside categories, but roughly these are the set of lines that can be triangulated on a surface. We can look at the example of Tori code. In Tori code, let's call A to be a set of lines There are 6 possible choices. So one is the trivial line, so it's a trivial surface. You take some sort of a closed surface and then you triangulate it with lines. So the set of lines you pick is 1, that's the first case, and then we can pick 1 plus e, in which case the multiplication is something like e times e is 1, and then you have 1 plus m. I'm just writing down all possible separable algebras in Tori code, or at least the simple versions of that. 1 plus f, and in fact it's this surface that implements the EM duality we were talking about. You take a surface and then triangulate it with the identity line, the fermion line, and now it acts by wrapping around other lines and it implements a transformation. So pictorially it's something like this. So this is the surface, something like that, and then there's a line E or M that's being wrapped by the cylinder, and then if you contract the cylinder, it will implement the transformation. So the cylinder extends as well. You get M line. The zero form symmetry acts on a line by like wrapping it in form of a cylinder locally and then contracting it. So this is the thing that implements the EM duality. And then we have these two things. It's something called a discrete torsion. So there are 6 simple objects in the category of surfaces of Tori code, which forms a 2 category. And one of the examples that we discussed was the EM duality of Tori code, which is implemented by higher gauging. This process is called higher gauging, where we pick a surface and then triangulate it with lines. It's obtained by triangulating a surface with a one line and then the emergent fermion. We can look at this case, and this case is a non-invertible symmetry. It's called SE. So SE is the surface corresponding to the algebra. And it's 30 minutes. Okay. Yes, indeed. Yeah. Yes. The simple ones. You can now like get other ones by taking direct sums of these. Yeah. Like these are the simple objects, but they're connected in 2 category of surfaces of Tori code. Yeah. So let's. Yeah. No worries, please. Well, a fusion category, the objects can be given quantum dimensions, but if you look at their fusion rules, you would see that there is no consistent way of giving them quantum dimensions. So this cannot be just a one category on the nose. And now since these are surfaces, there can be lines living between them, and the lines will form a one category. So it's a category which contains a category as simple objects. Thanks for the question. So let's look at SE, which is obtained by taking a surface in your space time and then condensing the 1 and E line on it. So let's study how the SE acts on the lines. So this is my symbol for acting. It's this triangle, RT triangle, ATEC. And it sends 1 to 1 plus E, so it's not leaving identity invariant. It sends E to 1 plus E. And then it sets M and F to 0. So if we were to write the surface as a matrix, it's going to look something like this. Yeah. Yes. Starting junctions. Starting junctions.
Yeah,
Mm-hmm. Yeah. Yes. Yeah. Sorry. Yeah. That is correct. Yeah. So this is what we get on the nose if we took the line on, say, a topology which represents your space-time, and then we actually computed it by contracting the surface, the high energy theory way to do it. And this is what we get. So it sends a couple of things to 0, and then it's acting in a funny way on the identity line. In fact, like in Matt's paper with Rajat, they kind of argued that these two are features of non-invertible symmetries. It will always send identity to identity plus extra lines, and it would send things to 0. So it sends it to a twisted sector, which is not being counted here because we are only looking at genuine lines in the theory. And as Brandon suggested, the way to actually compute symmetry action would be through the lasso action.
Like similar to
You include all the possible boundary conditions, not to define your theory.
absolutely. I
Exactly.
think he's going to give a more compliant story. Maybe.
Yeah. Yes.
It is so hard.
So you need the generalization of tubes.
Yeah. Yeah. Yes. It's just done. Yes. Just need to apply it. Right. So this is what the symmetry does naively. And now let's try to refine our analysis by doing the second step, which was adding twisted sectors. Now, SC has two twisted sectors. Let's label them X and Y. And it has two twisted sectors due to the same reason. But in this case, the reason is not so much as being left invariant, but we upgrade the fixed point theorem to the number of twisted sectors of a symmetry is equal to number of lines that have self junctions with the surface. And we proved it in the paper. So there are two twisted sectors because we can show that there are two lines that have self junctions with SE. And the proof of this can be done, the proof of this involves compactifying and then using arguments from 2D TQFT. But one has a line with it, one has a junction with itself. So this is roughly something like E comes out, and then the same thing for E. So 1 and E have a junctions with themselves on the surface. So there are two twisted sectors. And we can complete how the symmetry acts on all these lines now. And yeah, wait. So the argument is that M and F get sent to 0, but what's actually happening is that M and F are getting sent to the twisted sector. So by studying junctions, you can show that, okay, maybe I should use, yeah. So we can show that M and F have a junction with the twisted sector X. And this is what we was talking about. And this is also easy to see if we were to work out the anion condensation, 3s3 to dc2 side. And now the second question would be, how does the symmetry act on twisted sectors themselves? In this case, it doesn't, but it could. There is nothing driven. Sorry. It's yeah. So as I said, we simplified the problem by knowing the gauge theory and also using inputs from anion condensation. No, I would say no. In fact, yeah. No, no. Right. Yeah, and the question is what happens to SC acting on X and SC acting on Y. And even though we write down symmetry actions, one more thing that is not quite clear to us is this the unique representation of this non-invertible symmetry acts? There are some arguments from like using tube 2 algebras or 2 tube algebras and braided model categories, but we will not get into them right now. lines in the mm-hmm.
This thing gets yeah. I mean, some kind of generalization. Yes. There are also examples where you have general applications of branching.
Right. So I'll just state this here without proof, but the SE action on X, so far as we know, is then SE action on Y is 2Y. Yeah, because at least this case it's easy to motivate it, because SE is a self-dual surface, which means that if you just flip all the arrows, you would see that X going into the surface and then M and F coming out. So M and F also have a junction, and SE acting on X needs to have an X there, because otherwise you wouldn't be able to lift X to a genuine line in the gauge theory. X needs to have a subjunction. And so yeah, this is how the symmetry acts on like this extended set of lines, genuine and non-genuine. And now we can ask, what can you guess the gauge theory, similar to what we did for the Ising case? And yes, you can. Right. So let's denote the fusion category, or the one category that we have, by extending toric code according to the action of SE as some B. So B has the lines from the toric code 1E, M, and F, plus the two twisted sectors. For people in the know, this B as a one category is S1 plus SE module category over the record. Yeah, so we see S1 coming into play here, and in fact, this is one of the punchlines of the paper, which is, if you want to gauge its zero form symmetry, there is, you can think of it as gauging some sort of an algebra in the two category, and the algebra will always have an S1. So B as a one category is this thing, this is this comment, and now we can ask for fusion structures on B. That obeys, it should already obey the fusion of the toric code, because the genuine lines can always have their fusion from toric code. So first point is that yeah. So any module category or revision category corresponds to an algebra. I'm just denoting the algebra S1 plus SC. Yeah. So yeah, this corresponds to the algebra in an ostrich sense. Obeys the toric code, and then 2. Now we can use some inputs from the nature of the surface. So SC is obtained by triangulating a surface with 1 plus E. So what this would mean, that SC is the algebra object for SC is 1 plus E. This would mean that I can take an E line from the bulk. So say I have the two twisted sectors x comma y, one of them in the boundary, and then I have a C surface here. So what I can do is I can take an E line, bring it to the bulk of the surface, which would trivialize it, or I can take the E line and then fuse it with the boundary condition. But it's a topological process, so the two outcomes need to be the same, which would imply that SE should be equal to, the twisted sector should be equal to fusing something with the boundary, or Y tensor E. This implies that and you can also show that x tensor M equals Y, and then Y, sorry, x tensor F is also equal to Y, and vice versa. M is an order 2 line. So these are the fusion structure that we already know. So whatever overall fusion structure that we impose on B should satisfy these constraints. And a choice is the following. This is a choice. There is no like a priori way to calculate this fusion, which would be something nice. And in fact, if we take a modular tensor category which has a small number of finite objects and a surface which also has like small number of twisted sectors, we can in principle use the classification of low rank fusion categories to get a handle on the fusion structure. So this is a choice of fusion structure that we can impose. I have about 10 minutes left, so I'll try to wrap up quickly. Well, not rank 6. What you can argue that x times x has quantum dimension 2, so whatever appears here has to have quantum dimension 4, and it's also supposed to obey these constraints, which would kind of restrict this to a rank 3 problem. And in rank 3 you have repes 3 or cousins thereof. Yes. So for this choice, B can be written as some Z2 times repes 3. Bear in mind that there are also choices regarding F symbols and R symbols that go into this thing, which is part of the data that we have to specify. It's symmetry fractionalization and turning on an SPT and all that stuff. So this is going to be something like and again we can use the same formula to argue that if we gauge this symmetry, what we are going to get is that is cool. So, right there. This is the thing. You can figure out the gauge theory by asking for the following. So we compute something called Drinfeld center of this fusion category, and then we pick the part that's transparent to the toric code sector, and there is a motivation for doing things this way, and that can be explained with the following process. So say I have some sort of a 2+1d TQFT in the bulk. So this is supposed to be like a sheet, time is running outside, and this is filled with toric code. And now what I can choose to do is pick a part of the space-time and then gauge the symmetry corresponding to it. Anything. It could be the Ising, it could be the electromagnetic duality, or it could be this S1 plus SC, etc. I could gauge it in the half space, and this would create a domain wall between TC and whatever the gauge theory is. This is called half space gauging, and this domain wall, like quantum mechanically, it's going to be like a domain wall that allows particles to tunnel across. So anions or the lines in the toric code can pass through the domain wall at zero cost. It's a topological domain wall to go and become identified with lines in the gauge theory. And that is essentially what this formula is doing. So the B that we see there are the wall excitations, because this domain wall is going to be a 1+1d object, and there can be excitations supported on the domain wall. And this B is the fusion category of excitations on the domain wall. And now what we can do is employ the folding trick. So we can fold this around and get a boundary condition corresponding to the domain wall. Sorry? Yes, indeed. Yes, yeah, that is true. And then this domain wall will now become some sort of a boundary condition. And it's a theorem that works for like all TQFTs, like theorem in a physical sense, which was like written down by Liang Kong visiting the workshop, that if you have some sort of a boundary data that corresponds to a fusion category or like a fusion 2 category, fusion n category, you can take the center of it to get the bulk TQFT data. So if we have some boundary, it could be a QFT with some fusion category symmetry, or it could be a CFT, a 2D CFT, and it supports a bunch of lines on it having a fusion structure, then you can take something called a center to get the bulk TQFT out of it. So this is in some sense topological holography, or SymTFT, goes by a lot of names. And that is what we just did, this formula. But recall, we see that the bulk theory that we will get from folding is actually toric code times the gauge theory, and we only want the gauge theory part. That's why we check lines that are just transparent to toric code. Right. So this is how, so if I now apply that formula for this B, then I would get the gauge theory to be center of rep S3, which is this mathy way of writing S3 finite group gauge theory. Okay, let me just mention a couple of things. One is that these domain walls are really useful when it comes to understanding the nature of symmetries and the things that you can and cannot gauge, because you just need to know the way back, which is anion condensation, and then you can decode properties of the domain wall, and using these domain walls you can prove theorems about the kind of stuff that you can gauge, you cannot gauge, and yeah, that's what we do in the paper in addition to doing examples. I think that's a good point to conclude. Are there any questions? I would say very, because in the invertible case, a lot of in the invertible case, a lot of precise statements that were made use the fact that it's a modular tensor category, and that helps you when you want to compute anomalies of symmetries and things like that. And I would expect the same thing to hold for non-invertible case. We do use like the non-degeneracy of braiding quite a lot. But if you don't have, if you have a braided tensor category that's degenerate, then the mod B is going to be non-trivial, the Drinfeld center of mod B. There's going to be like a 4D TQ.